When you watch the video of the Challenger disaster, you can see at about 72 seconds after takeoff, things start to go to pieces. The right side solid rocket booster comes loose from the ship and smacks into the main external fuel tank. The fuel tank comes apart, dumping a huge amount of hydrogen into the atmosphere. From here, the ship is engulfed in what the accident report calls, quote, a massive, almost explosive burning of the hydrogen streaming from the failed tank bottom, unquote. Then the ship breaks into pieces, which you can see here streaming away with their own smoke plumes. As we continue the video, you can see both solid rocket boosters roaring off under their own thrust. Suddenly, both explode. This is not an accident. It is a system built into every rocket launch that can be activated to explosively destroy the craft if necessary. We saw a similar system swing into action on the recent SpaceX integrated flight test. After that ship lost control and began to tumble end over end downrange, someone or something sent a self-destruct command. Now, there is some debate over whether SpaceX's system failed to immediately end the flight. If so, this would be the only widely known failure of a self-destruct system. Chemical rockets operate on the hairy edge of so many spectacular failure modes that it's usually not hard to tip them over the line. Throw in explosively driven penetrators and failure is quite certain. These self-destruct mechanisms are called flight termination systems, or FTSs for short, and they amount to an array of radio-controlled explosives mounted to the rocket's engines. When a rocket is powered by liquid fuel, such as this Antares 130 launch in 2014, you can quickly blow the whole thing to bits by cutting open the liquid fuel tank and dumping it into the rocket's exhaust. The cut can be accomplished by explosively driven shape charges. Commercial companies offer systems to create a detonation wave, route it through a cable, and apply it to an explosive fixture that fires a penetrating jet into the skin of the tank, slicing cleanly through. These systems can be circular, sending Mach 10 plus jets into the tank from all directions around the outside, linear, launching a straight sheet of molten metal to cut a line, or simple point charges that create a giant hole. In ships like the Challenger or this Ariane 5 that use solid rocket boosters in addition to liquid fuel engines, a linear-shaped charge array running down the side of the tank opens it like cutting the casing on a sausage, dumping the fuel out in hopes that it will not catch fire. After Challenger, which we'll get back to in a second, NASA decided to require a system to terminate thrust of a solid rocket booster by dumping its fuel rather than igniting it, giving the crew time to escape. Its cancelled Ares 1 and current Artemis 1 solid rocket boosters use explosive shape charge systems running the entire length of the tank to implement this thrust termination. FTS units on ships that use nastier propellants like hypergolics are required by US law to initiate burning of the fuel in an attempt to avoid dropping it on people. Some other countries aren't so nice. Hypergolic propellants burn spontaneously upon contact of the fuel components, so igniting them in a termination amounts to simply blowing out the walls between the tanks with a high explosive charge, allowing those fuel components to mix. Now, having radio-controlled explosives strapped to what is essentially a giant bomb sounds like a risky situation. Can an FTS be activated accidentally or by a third party? Good question. NASA requires that FTS modules use command uplinks, or GO signals, with, quote, NSA-approved or endorsed techniques and products, unquote. The Space Force Requirements Manual details some of the design, logic, operating frequencies, and other details of the FTS, but keeps it vague enough to blunt potential hacking. Errant triggering from the ground is one potential problem, but what about the onboard HAL 9000 deciding that humans are superfluous to its goals?
I'm sorry, Dave. I'm afraid I can't do that.
In recent years, autonomous FTS units have been developed. On many newer unmanned ships, the explosives can be fired by the onboard computer under certain conditions. Now, that may be the future, but in many cases, including flights with a crew on board, this responsibility is still held in the hands of another human. This human, the range safety officer, has the authority to engage the system and terminate the flight if one of a few things should happen. Known as the RSO, his primary mission is to keep people and things downrange of the launch out of harm's way. Operating by the rules, the RSO estimates the chances in 1,000 or 1,000,000 of loss, injury, and death on the ground from the evolving situation. The RSO is explicitly authorized to push the big red button in one of three circumstances. First, is the vehicle traveling outside the box of airspace in which the mission is supposed to operate, referred to as violating a flight termination boundary. Now, this is some silly, overly neutral engineering jargon for a very bad place. Second is losing communication with the vehicle so that its location is unknown, but can hit the flight termination boundary, or the vehicle is taking an obviously erratic flight path that indicates total loss of control. And finally, the RSO is given carte blanche to terminate if, quote, other mission-specific conditions present rationale for additional criteria, unquote. That all sounds fine for a ship carrying a satellite or some other inanimate cargo. But what about launches with people strapped in the nose cone? Can those be blown up too? Well, yes, but there is a caveat. NASA requires that ships carrying astronauts contain an Earth Ascent Abort system, that is bureaucracy speak for some way for astronauts to escape a disastrous launch. It's designed to violently propel the crew compartment away from an escalating disaster. This is intimately tied to the FTS. The crew escape system can be triggered by the arm or fire command from the flight termination system. It's fascinating that these launch abort systems have come into play several times on manned missions. Challenger sadly had no crew escape system, a famous failure of the NASA safety culture in the 70s and 80s. But 3 Russian Soyuz missions successfully did manage to liberate astronauts as their ships blew up. Crew escape systems are worth an entire separate video, but these rare events are so interesting that we should quickly touch on them here. Soyuz T-10, launched in 1985, caught fire on the launch pad just before liftoff. A set of solid rocket motors in the tip of the rocket blasted the crew capsule away just 6 seconds before the fuel tanks exploded. The crew accelerated vertically to near Mach 1 in seconds, in the process pulling an incredible 14 Gs. Medical treatment, of course, limited to vodka and cigarettes. In 2018, the same system saved the men aboard Soyuz MS-10 after a stage separation failure destroyed their ship high in the atmosphere. And the Soyuz 18, launched in 1975, experienced a catastrophic failure during ascent. The crew underwent a harrowing suborbital journey to miraculously survive. Things were so bad that the escape system was destroyed before it could even be used. And that's another story for another day. And that pretty much covers it. Modern rockets, including those carrying astronauts, all take off with their own self-destruct systems on board in order to stop a failed launch from raining death and destruction from above. Rules, regulations, and codes apply to those devices, but ultimate control to terminate the mission often still rests under the finger of the RSO. I hope you found this video informative. Please stay tuned for more upcoming videos on other interesting aspects of space, science, and technology.